This is the Insurance Institute for Business and Home Safety's Disaster Discussions podcast, where we explore the intersection of weather and the built environment. Welcome to the Disaster Discussions podcast. I'm your host, Rachel Penton-Goche. In the early morning hours of Christmas Day, 1974, the city of Darwin, Australia, located in the country's Northern Territory, experienced a direct hit from Category 4 Cyclone Tracy, with the eye of the storm passing over the city between midnight and 7 a.m. A wind gust of 217 kilometers per hour, or 135 miles per hour, was recorded by the Bureau of Meteorology anemometer before being destroyed. The impact that Tracy had on Darwin was profound, with 90% of the city's homes becoming uninhabitable overnight, leaving 41,000 of the 47,000 residents homeless. 2024 marked 50 years since this historic storm, and today the fingerprint of Cyclone Tracy is on houses across Australia. The immense tragedy sparked an overhaul of construction practices and building codes across the country. Joining me today to help tell the story are this month's podcast guests, Dr. Geoff Boughton, Adjunct Associate Professor at the James Cook University Cyclone Testing Station, and IBHS's Dr. Korah Parackal, Research Engineer and Adjunct Senior Research Fellow at James Cook University Cyclone Testing Station. Welcome to the podcast. Yeah, Geoff, of course, joining us all the way from Australia. So as one of our special guests today, we'll let you start out. Just tell me a little bit about your career path and how you became a wind engineer.
Yeah. Completely by accident. So my career path that I was a geotechnical engineer. I was working in the Northern Territory at the time, building airstrips in remote communities on an island not far from Darwin. And Cyclone Tracy happened, intervened, and I worked in Darwin for quite some time after that as part of the cleanup operation, and it effectively changed my career. So I then sought work in the industry that was looking after buildings, started with the Cyclone Testing Station in 1981 as a research fellow, the same position that Korah occupied for some time, and have worked off and on with them since 1981, and now am effectively full-time with the Cyclone Testing Station.
And we're going to get more into that great story a little later about how this storm changed your career path. But Korah, I want to hear from you as well. Tell me a little bit about your career path and tell me how you and Geoff know each other, by the way.
Sure. Yeah, Rachel. Really good to be here. It's now been almost 3 years here at IBHS. I also got into wind engineering also by chance in many ways. So I started my career journey at the University of Queensland. I studied civil engineering over there. I moved back home to Townsville and was looking for a bit of part-time work. And I got a part-time job at the Cyclone Testing Station as a research assistant, tubing up wind tunnel models and so on. And that's I guess, where I caught the research bug. Worked in Singapore for a little bit as a structural designer, and then came back to Australia to work on a PhD there. And Geoff was actually one of my mentors during my research degree. So that's how we know each other, and we've known each other for quite a while.
The other thing is that we worked on damage investigations together, and there's nothing like climbing through the wreckage of a building alongside someone for a fortnight at a time to get to know them really well, to trust them, and to understand the way they work. So that was pivotal in our really close working relationship, wasn't it, Korah?
Yeah, absolutely. And I think eating tinned spaghetti on the back of a truck or a ute, that's part of the experience of doing a damage survey together.
Yeah, and for me, cold shaves on the rearview mirror of the ute as well.
Wow, nothing like bonding time, like being out in the field, right? And
correct.
In these conditions. We want to talk about Cyclone Tracy first, and there just are a few differences that we have to kind of put on the table here, since we are talking about a Southern Hemisphere storm. So it's in the Southern Hemisphere, cyclone season runs from November 1st to April 30th each year. That is the opposite of our Northern Hemisphere's June 1st to November 30th season. Hurricanes spin counterclockwise in the northern hemisphere, while in the southern hemisphere, tropical cyclones spin clockwise. And this is due to the Coriolis effect, or the apparent force that causes the deflection of an object moving on or near the Earth's surface, such as wind and air currents, due to the rotation of the Earth. So according to the Bureau of Meteorology, the most cyclone-prone area of the country is the northwest coast. Also, Queensland and the Northern Territory also get a high number of tropical cyclones. And on average, about 11 tropical cyclones form in the Australian region each season. So there are quite a few notable storms, historic storms for Australia, Peter, Katrina, Yasi, but Cyclone Tracy, often referenced as one of Australia's worst natural disasters. So talk about Tracy. How is the storm, viewed in the culture of Australia when people are, referencing some of those more historic storms?
Yeah, we've just had the 50th anniversary of Tropical Cyclone Tracy, and it's been quite a landmark event, 50 years since that. A lot of people who were associated with it met in Darwin 50 years after the event. The insurance industry has a large focus on 50 years ago, we discovered this peril and the magnitude of the peril. People had died in Australia in tropical cyclones well before Cyclone Tracy. But to lose 66 people in a city environment in a few hours because of a natural event like that, that was relatively new for Australia. And people's perception that their home is their castle, they'll be safe in their castle, they'll be safe in their home, that was shattered on that night. And as a result of that, there was a substantial effort at all levels of government to try and improve things for people, to improve community safety, improve community cohesiveness, because along with the damage it did, it destroyed a community. As you rightly said, there were 47,000 people living there, and 41,000 of them were homeless in a few hours. So that meant a mass evacuation of a whole city to take those people to other parts of Australia, and they were scattered. So it was like the population of a city was spread all over the rest of the country, and that fabric, that community cohesiveness was completely lost. And we don't want that to happen again. So that it galvanised from the Prime Minister, our head of the national government, all of the way down. People were saying this must not be allowed to happen again. And engineers were on the forefront of that.
Right. We're going to compare Tracy to a U.S. storm a little later on when it comes to building codes, but just the storm for the United States that comes to mind is Hurricane Katrina. I used to work in Louisiana, and that's the only storm where there was a mass evacuation of, to the size, I think that is comparable to Tracy, where, portions of an entire major city were uprooted overnight due to one storm. So certainly drives home the devastation and the impact and severity of the storm. So I want to get into get into Cyclone Tracy, what it was like. Korah, you weren't around for Cyclone Tracy, but Geoff, you were there, and we're going to get your firsthand experience on that storm and what it was like. So Tracy was the first cyclone landfall for Darwin in 40 years at the time, a slow-moving storm moving at only about 4 kilometers per hour or 2 miles per hour as it approached. And it was described as a very small in size, but tightly wound storm. So just kind of describe, Geoff, the lead up to Tracy's landfall and talk about the forecasting of this event. Were people aware this was coming, and what was that like?
Yep. A very important issue here is a cyclone called Cyclone Selma that generated off Darwin in early December. So it generated, I think, on December 1, but it hovered around Darwin for quite a while, and there were warnings about that particular cyclone. The skies got very cloudy. It looked pretty threatening, but the cyclone just hovered around and then disappeared. So people felt, we've had one already. It created muggy atmosphere. And then when the warnings started coming for Cyclone Tracy, people were thinking, yeah, we've been here before. It's Christmas Eve. And a lot of people didn't probably pay it as much attention as they would have had Selma not happened, and this being the first warning that they experienced that season. And also, if it hadn't been Christmas Eve, where there were quite a number of other activities happening. Now, I've had a North American Christmas, and an Australian Christmas feels quite different to a North American Christmas, because over the Christmas period, that's the start of our long holiday season. So that the time leading up to Christmas is the end of the year. It's the end of everything. People pack up and go away, so that there's a finality, if you like, leading up to Christmas. And people were enjoying end of year parties and those types of functions, which is part of, if you like, the Australian culture of Christmas. So it's more than just a day. It's the end of one era and the start of a next. So it occurring on Christmas Eve was fairly significant, because people were mightily distracted by those normal end-of-year functions. In the Northern Territory, there was, people call it a party atmosphere. The outdoor living and the pleasant climate of the Northern Territory led to many parties, gatherings, outdoors. There was a noise in the evenings, most evenings, of people just having fun, sharing time outdoor on their balcony or under their house, so that they were the normal kind of activities in a Darwin evening. And people weren't necessarily looking at sacrificing on this special day. So there were a couple of things that led up to perhaps a little bit of viewing it as not such an important warning this time. Nonetheless, when the event arrived, it arrived very quickly. As you rightly said, it was a very small storm. The radius of gale force winds was only 50 kilometres across, which is really, really tight. But it packed a punch right in the middle, and that enabled a couple of things to happen. The seaward approach to Darwin is fairly narrow. The cyclone steered its way between an island and a headland. And had it been a really big cyclone, it might have got started losing strength. But because it was a really tightly knit one, it was able to navigate that tight passage, and it scored a direct hit on Darwin. And again, a tightly wound cyclone just missing Darwin would have almost been a non-event. But because it scored a direct hit on Darwin, that's why there was such significant damage. The other thing that you mentioned is that it was moving relatively slowly, and it was. So normally when a cyclone moves relatively slowly, you get this long build-up into the cyclone. So for a large cyclone moving relatively slowly, you get this big build-up, and the winds increase gradually over a period of time. So people can say, okay, it's starting to get uncomfortable, I'm going to seek shelter, and then they've got time to do something about it. But being such a tight storm, it caught a lot of people by surprise. They were enjoying themselves, having fun, and the sky's getting more gloomy, but then suddenly it gets windy. Suddenly the driving rain is really, really punishing, and they haven't got time to do much more than crawl into the bathroom and grab a few things around them. So that those were things that led up to the trauma, I suppose, that the city was subjected to. And I can remember dealing with people after the event, and they were vacant, and they were exceedingly traumatized by what they had been through. They were staring long into the distance It really was quite confronting, and the effect on people was very significant. And as part of the evacuation, Australia is a really large country, and Darwin's in a really sparsely populated area. So when we talk about evacuating Darwin, it's not people jumping in their car and driving to a nearby city. It's them hopping into a Starlifter and being flown across the country to a state that they may never have visited to. And they're now 3,000 or 4,000 kilometres from where their home was. Also, because it was the start of the holiday season, a number of people had left Darwin. So they'd packed up their home, they'd gone to visit relatives in other places, and they no longer had a home. They no longer had a place to return to. All of their stuff had gone. Whatever they had on a holiday, that was it. That was their life from now on. So in terms of disruption, it was a really, really, really major disruption for that community, which had been a jolly, happy, almost carefree, party atmosphere type community, and suddenly it was completely dispersed, and that cohesion was totally destroyed.
Right. So many different factors that had to come together just right, that did come together just right to make this such a devastating event.
Or maybe just wrong.
Or exactly, maybe just wrong. You're exactly right. I mean, here in the U.S., it's winter time here, but still, that's, the 1 week of the year where I think everything just, if it's going to shut down, that's the time it kind of shuts down. People tend, I think, to steer clear of the news and just, it's your 1 week to relax. So this is just horrible timing on when the storm made landfall. So Geoff, you were actually on Korah Island. You were working as a student, and this island is about 250 kilometers northeast of Darwin, and you were giving weather reports over the radio as the storm started to move into the area. Tell me about that.
Yeah, well, these remote communities had weather stations on them, and we had to do twice a day skeds or send the data from the remote weather station into the Weather Bureau. And of course, it worked both ways, so that when there were warnings given, they would send warnings out, and we'd be sitting on our radios listening to those warnings and plotting up the data on our sheets, our maps, showing where the cyclone was and where it was heading and what their extent of warnings were. So, yeah, it was a time when we were monitoring things, we were listening to what the warnings were. The warnings were relatively detailed. Cyclone Tracy did quite a tight turn to line up on Darwin, and that turn was predicted, but maybe not to the extent that it actually happened. You've got to remember, this is the 1970s too, where satellite technology was right in its infancy, and a lot of these predictions were made from surface obs, returned in by radio at our regular schedules by outstations like the one on Korah Island. So they were assembling all of this information, looking at it all together and saying, oh, with this atmospheric pressure, we've got these factors driving the cyclone.
Right. So what was the experience like for you as you were on that island? You didn't experience a direct hit from Tracy, but you still experienced some of the wind. Is that right?
Yeah, we still experienced some wind and rain, yes. And yeah, we also lost communications, so that as part of the cyclone, our radio tower blew down. So that was quite significant. We were without communication after Cyclone Tracy, and a plane did fly over just to check on what was on the ground, so that we did feel people were watching after us, but we had no idea even what happened in Darwin, because we didn't have any communication with the outside world until we'd rebuilt the tower.
So how long were you on the island after the event? How long was it before you realized what had happened?
About a week. So
About a week.
about a week after the cyclone, I was able to leave on a plane, go into Darwin, and work in Darwin as part of the cleanup operation.
So I want to turn to the aftermath of Tracy, and I just wanted you to kind of tell us, what did it look like? I know that 90% of the homes become uninhabitable. A huge cost as far as the number, the damage numbers. Estimated 400 to 500 million, which is 2 to 4 billion in today's dollars. So what did you see when you got back to the mainland? What did it look like?
Yep. And first up, I'll paint a little picture of Darwin prior to the event, a physical Darwin prior to the event. It was a tropical city with lots of large trees. It was a leafy green city. Houses were embedded in a lot of trees in some of the more mature suburbs. The new suburbs were a little different. The houses were just out in the open, and the new trees hadn't grown. But by and large, it was a leafy green tropical city where you heard birds all the time. The air was warm and pleasant, and people spent time living outdoors. When I returned, there were no leaves, so that all of the leaves had completely gone. The trees were bare. In many cases, all of the smaller branches had gone too, so there were skeletons thrust up into the sky alongside places where homes used to be. Many of the homes were what we call a high-set home, so that the floor was about 3 meters above or 2.5 meters above the ground. And in a number of cases, all that was left were the floorboards, and they were clean. There was nothing on top of them. So it was really, really eerie. Now, if you're removing all of that stuff, it's got to go somewhere. And it was just scattered. So wherever you looked, there was wreckage. Some of it was identifiable, so you could occasionally see a roof truss. But in many cases, it was just collections of twisted, mangled, tortured iron that was the roofing that was used there. So nearly all of the roofing was sheet roofing, and it was corrugated, and sticks of timber, because most of the buildings were timber framed. So it was mashed up sticks of timber and twisted, tortured sheets of roofing iron. And it was quiet. It was quiet because everyone had gone. There were no kids. You'd occasionally see a kid's toy, which was just eerie. And in going about the suburbs, you'd occasionally smell something really foul. And you'd think, oh, God, what's that? And you'd try and sniff it out just in case it was something that you had to deal with. In many cases, it would be rotting food, the contents of a refrigerator, in some cases a pet. But it was overwhelmingly quiet, desolate, and full of wreckage. Just looking at it, there was an overwhelming feeling that there has to be a better way of doing this. And if anyone knows a better way of doing this, it's going to be an engineer. And I was a student engineer, and I thought, okay, I can use my skills to try and improve this situation. As I was putting stuff into the back of a truck to take it out to the tip, I was looking at where the failures were occurring. What are the things that have gone wrong? But at the same time, there were experienced researchers doing what I now do, going through this wreckage and trying to identify where the problems were. And the person who became my PhD supervisor was leading that team. I didn't know him at the time, and maybe our paths crossed while we were in Darwin, but I have no recollection of it. But they were specifically looking at what had gone wrong with that housing. And there were a couple of things that had happened previously that meant nothing should have gone wrong. Darwin was very much a government town. So a lot of the housing had been built by the Commonwealth Department of Housing and Construction. So it had been designed and constructed under tight supervision to resist what they thought the wind was going to be able to do to those places. Now, as context, a couple of years before Cyclone Tracy, in 1970, there was a cyclone in North Queensland that hit the Whitsunday area of Queensland called Cyclone Ada. It was a Category 3 event and it did a reasonable amount of damage to houses. And at that stage, the young James Cook University had some civil engineers who went down and had a look at it and found a few things that had gone wrong. And a number of people thought, oh, okay, in that area, the builders just don't know what to do. And an education program was put in place to educate those builders. And then a year later in Townsville, which is where the James Cook University is headquartered and Korah lived when he was last in Australia, another tropical cyclone happened. It was also a Category 3 event, and that was Cyclone Althea. Townsville was a much bigger city, and it did a significant amount of damage. And it was right on the doorstep of the then young James Cook University, and they did an investigation to find out what had gone wrong, and they told the engineering community about their findings. And part of the engineering community was the Commonwealth Department of Housing and Construction. They incorporated those findings into the new houses that they were building in Darwin. So that 3 years later, there were new houses in Darwin that had been built based on the experience of what had happened in Townsville. So people were thinking, yep, these houses have got to be okay. They weren't. They were just like all of the others. And so when George Walker, who was my supervisor at James Cook University, went to lead the investigation in Darwin, they were looking at details that they thought would be okay after their experience in Cyclone Althea. So it was really important for the engineering community to say, okay, we didn't get it right. We've got to find what has gone wrong. And that they did. They were looking through a very fine lens at what they were seeing, came up with three main things that they felt could be improved significantly after Cyclone Tracy. And those three main things formed the cornerstone of plans to rebuild Darwin in a different way. And because it was a Commonwealth city, because it was highly organised, they created the Darwin Area Reconstruction or Building Manual to guide the reconstruction. So Cyclone Tracy happened at Christmas time. By May, this manual was in place that guided the reconstruction in such a way that it was going to be much more resilient and able to cope with wind loads much better based on that technical research work that was done immediately after the event, identified those three shortcomings and put in place stuff that was going to mean that buildings were going to survive much better in the event of high winds in the future.
One of the findings that Geoff mentioned of that report from the damage survey that was done in Darwin was that fatigue, low cycle fatigue, was a real problem. So Geoff described the mounds of corrugated metal that were strewn across Darwin. So that corrugated metal was originally roof cladding. Roof cladding in Australia is very often corrugated metal, especially in the tropical parts of the country. And if you would imagine a paperclip that you just hold in your hands and you bend it back and forth a couple of times, eventually it becomes a bit brittle and it'll snap very easily. And the same thing can occur with the very thin pieces of metal, the thin sheets of metal, and how they're fastened to a roof. So when you have these rapid fluctuations of pressure on the roof due to the wind, the turbulence, the eddies and vortices that streak across that roof, that loads and unloads that roofing cladding over and over again, thousands of times. And the screws that fasten that roof cladding into the rest of the roof structure, just around those screws, it's just like that paperclip, these star-shaped cracks can start to emerge due to being loaded and unloaded over and over again. And eventually that metal cladding will pull over those screws. And that's fatigue happening in action during a storm. And since then, there's been a lot of research being done in Australia to how to mitigate those effects in roof cladding, including the types of washers that we use, the type of metals that we use, and so on. And a test that came about from what the observations of realizing fatigue was such a problem is called the low-high-low test, which is something that is one of the types of commercial tests that's done back in Australia and at the Cyclone testing station. So here, a piece of roof cladding is installed in a pressure box, and that's inflated and deflated over and over again to simulate pressure on that roof due to the passage of a storm. And you subject this to maybe around just over 10,000 or so cycles. We load and unload that roof over and over again for a large number of, say, low intensity cycles. We gradually ramp up the intensity until a peak, and then we gradually ramp back down again. And this is to simulate the passage of a cyclone over a building. So as a cyclone might approach a building, that wind speed is increasing and increasing, and then as it passes away, it decreases and decreases. And so, you could have a situation where the roof of a house has survived the peak loads, the peak wind speeds during a cyclone, but afterwards, even though that you might have low wind speeds, you can still have a failure because that roofing metal has been bent back and forth over and over again. So that's why I have this ramp up and then ramp down of pressure, which is what's part of what's called the low-high-low test. And this fatigue test is actually one that's it's used quite particularly in Australia. It's actually something that we could really learn a lot more from here in the US. Currently, our metal roofing cladding that's used here is not designed for fatigue loading in this fashion, including a ramp up and a ramp down of loads for such a long duration.
And the second thing that came out of this report was that homes need a continuous load path, or as you say in Australia, the tie-down chain. Korah, just talk about what this means.
Right. Yeah. So this was the second item. The key finding from there is that you need that continuous load path. It's a very engineering term to say load path, and this is what we really mean is any structure has to get any forces, any load that's on the roof or any other part safely all the way down to its foundations. That's what makes a structure stable and strong. And Geoff alluded to this a bit before. A house is typically designed, or what used to be done is you're building the house to hold the roof up. You're holding the weight of the roof up during its normal life, but that's not what it needs to survive during a windstorm. You need to hold the roof down under extreme winds. And so the load path is in some ways reversed. It's as though you've turned the house upside down, perhaps even hung a few cars off it and then shook it very violently. Those are the kinds of forces that a house needs to survive. And to ensure that continuous load path, each of the connections in the house has to be securely fastened. So if we look at a house, a light frame timber house, which is how we generally build houses here in the United States and also in Australia, and we took away all the wall cladding and the roof cladding, you'll see a skeleton of timber members in there. And if you look in that anatomy, that skeleton there, the load path that you need to follow is that any force on the roof has to go into the sheathing or the battens. Then it has to go into the rafters or the trusses. From there, it has to go into the walls. And from there, it has to go into the floor and the bearers and then into the foundation. Every one of those stages or any one of those parts of the skeleton or the anatomy of the house has to be securely fastened together. And that's what we mean by the load path. And in Australia, we call it the tie-down chain. And the reason why we call it the tie-down chain is that it is the weakest link in the chain that is the vulnerability of the house. You can have a strong chain in every other place, but if one of those stages is weaker, that's where the wind will find the vulnerability in a house. And that's really the key part of engineering a timber house, a light frame structure, or any other building for wind load.
And the third thing is design homes for internal pressures. So previously, homes had only been designed for external pressures, not high internal pressures. And it was determined that houses needed to be structurally engineered so that the roofs would stay on even when a window was broken. And Geoff, explain what this means for a home to be designed for high internal pressures.
Korah's already outlined the chain of strength, the tie-down path that is holding a roof down. It needs to hold a roof down because when the wind is going up and over the roof, it's actually pulling the roof upwards, so that the wind over the outside of the building is tending to pull the roof upwards. And in fact, on a house, the only wall that is not being sucked, or the only part of the building that is not being sucked out of the building, is the wall that is facing the wind. So that the wall that is facing the wind has to resist the direct impact of the wind, and the wind is trying to push that wall into the house. The back wall, the side walls, the roof are all being pulled away from the house. If there's some wind-borne debris in the airstream that hits the house, it's only ever going to hit that wall that is facing the wind, the wall we call the windward wall. So if it were to hit that wall, it's going to smash windows, blow in doors, break the cladding perhaps, and create a hole on that wall. That wall is the one that's being pushed into the building, so high-pressure air is going to get inside the building. Once it's inside the building, it's pushing outwards on every surface. That includes the roof. So while we've got the roof being sucked off the top by the wind going over the roof, when we have a window or a door being smashed, that instantly causes pressure inside the building that's pushing up on the underside of the roof. That adds to the suction on the upper surface of the roof, and it can almost double instantaneously all of the load in that tie-down chain that Korah was talking about. When that happens, if there is a weak link, it will be found. And that's what happened in Darwin. So that in Darwin, in Cyclone Tracy, we weren't aware of the fact that we could get this almost doubling of force when windows break. Since then, we're now really aware of it, and we design for the force that's going to happen on a roof if the windward windows are broken by wind-borne debris. And we have to do that as part of our codes and standards for all cyclonic areas of Australia. So it's a lesson we learned in Darwin, but we've applied it to every other cyclonic area across the whole country. And in looking at the post-Cyclone Tracy houses built since the 1980s, less than 3% of them experienced damage in Cyclone Yasi, which was arguably a bit stronger than Cyclone Tracy. So that we know those changes that have been made do serve to protect communities, do keep communities tighter together. If you're losing houses less than a few percent of houses in a community, that's not a huge dislocation. Often those people can still be accommodated within the community and the community remains intact. So to that end, it has been a success. We have, by working together as an entire industry involving engineers, building product suppliers, regulators, we've been able to protect communities to the point that we're able to say, yes, communities have a lot more resilience to these events now than they did prior to Tropical Cyclone Tracy.
And I know there are some caveats to designing homes for high internal pressures. Geoff, talk about some of the caveats and talk about any perceived negative aspects surrounding this.
Yep. In the early days, it was clearly identified that windborne debris was part of the problem. And so the caveats are that if we protect all of the fragile openings from windborne debris, then we can design for lower internal pressure. However, there are some elements of a house that it's really hard to even get a wind rating for, and an entrance door is one such element. So that for an entrance door, you might buy the door from one supplier, you might buy the latch from a different supplier and the hinges from another supplier, so that it's never ever tested as a system. And it's really hard to combine them in a way that we can say, oh, we know this is going to be able to resist a Category 4 or 5 cyclone. So that even though we might protect every opening with debris screens, there are still some elements of the building fabric that we can't say for sure are never ever going to blow in or be knocked in by some debris. So that this is one of the weak points, if you like, of that caveat, that we might protect everything with debris screens, but still have a door blow in and get that internal pressure. And if we haven't designed for it, then we will lose the roof.
And contrasting with the United States, this is really interesting to me. We still do not design homes to withstand these high internal pressures here in the United States, which is a big difference between the U.S. and Australia. Instead, we do rely on that debris protection, like those windows and doors to keep the internal pressure out. Korah, in Australia, you assume the windows will break, the doors will be blown in, but that the home will still be able to withstand these pressures. So contrast that. Why do you think we don't design for high internal pressure in the United States yet?
Right. I think it is very much a design philosophy thing. This is in many ways what has been established as what engineers do here commonly. It's all about protecting that building envelope. If you look through the model building codes that are used here in the United States, they emphasize the importance of maintaining the integrity of that building envelope. Which, as Geoff said, it does have some issues with that, right? You're relying on that envelope to actually keep the roof on in some situations, right, or in most situations. So it really emphasizes how important it is to have debris-rated windows where they are required, or wind-rated openings such as garage doors and such in the United States, because you're actually relying on that envelope to hold the building together. It's a key part of engineering design over here. And we do quite a lot of science communication about the importance of wind-rated openings, and this just emphasizes how important that is.
We do. We are big proponents of the wind-rated garage door here at IBHS. I want to talk about a U.S. storm that It sparked some similar changes, not nearly as stringent as the changes that Tracy sparked. But I think our comparison here in the United States is Hurricane Andrew. We saw this make landfall in Florida in 1992 as a Category 5 storm. This caused $27 billion in damage. And this is really a storm for the United States that sparked really our first major building code changes. So post Andrew, we saw the South Florida Building Code come about. That was enacted in 1994. And then it wasn't until 2002 that we saw the first statewide code adopted, which is the Florida Building Code. And today, Florida does have one of the strongest building codes in the country. But unlike Australia, we still do not have a national building code here. Building codes are left up to individual states. We know that not all states have a statewide building code, and even if they do, they're not always enforced. So that's quite a big difference between the United States and Australia. So of course, we work in the building code space here at IBHS, but that's really part of our work here at IBHS is to use the science to go above and beyond codes, give people choices that they can make to strengthen their homes, in the absence of a code. So I want to talk, Korah, a little bit about our fortified standard. This is our voluntary beyond code construction standard. Based on our research, it is very similar to the Florida Building Code. We often say the Florida Building Code is fortified-like. So this really puts the power on a homeowner to strengthen their home no matter where they live. So how does our fortified standard compare to Australia's wind loading standards? What are some of the similarities and differences, Korah?
Sure, Rachel. So like you said, the fortified standard, it really helps people in the U.S. navigate the multitude of regulations in every different part of the country. So being able to get that fortified designation really is a mark of quality in construction and performance there. How it compares to, say, the Florida Building Code and also the Australian Code, the common theme there really is about having that tie-down chain, that continuous load path, right? This is the essence of engineering a house to severe winds. It's ensuring that load path is there from the roof all the way to the foundation. Just like what Geoff was describing before, the fortified standard, to get that designation, an engineer does need to sign off to have that continuous load path. The differences, you could say, are one, there's less of a design for fatigue for metal roofing, and also internal pressures. That's something that all codes in the U.S., including the way the fortified standard works, can learn from. On the other hand, things that the Australian code can learn from is the way that fortified goes beyond just life safety, right? So the Australian standard focuses on structural integrity, keeping people safe in their house, but not necessarily being able to use that building or return home or live in that house after a storm. And a lot of this is to do with water coming in. You can have huge amounts of water coming in through the roof of a house or windows and such, even if there's very little structural damage, and that can make a building unlivable or unusable for weeks afterwards. The fortified standard goes beyond the Australian standard and also the Florida Building Code in specific details in the way the roof deck is sealed to keep water out. And this is a really great thing. This is a code for resilience as well, not just strength and engineering strength, which I think building standards all around the world can really lean on more.
I want to talk more about the Cyclone Testing Station, Korah. Before joining IBHS, of course, this is where you were located. So tell me a little bit more about its mission and kind of compare it to IBHS, some of the differences between your facility there and what we do here at IBHS.
Sure, Rachel. Yeah, the Cyclone Testing Station, actually, it's a place that's actually very dear to my heart, because that's where I learned my skills as an engineer and as a researcher. And Geoff gave us a little bit of the origin story of the research that was being done at JCU, James Cook University at the time. There was also some research going on in Canberra at CSIRO, so that's the Commonwealth Science and Industrial Research Organization. And so after Tracy, really that was a catalyst moment that we needed a dedicated institute to do wind engineering research in detail. And that was the birth of the Cyclone Testing Station, with staff who are based at JCU and also CSIRO who came on board at that time. And really, you might ask, what is the fuss about doing in-depth engineering research on a house, right? It's just a simple structure with some timber fasteners, timber members, roof cladding, but that's not the case at all, right? From an engineer trying to figure out how a house behaves, it is really, really complicated to understand where forces go within a house, especially as it starts tearing apart. It's extremely hard. And so that's why we needed this facility to do this in-depth testing specifically on houses, and also specifically to test these buildings in full scale. So the Cyclone Testing Station really was one of the first places in the world to test buildings under wind loads at full scale. And Geoff was actually involved in some of those very first tests there. The mission of the CTS is quite similar to IBHS, but a little bit different as well. It's all about wind engineering research, so understanding the fundamentals of how wind behaves as it moves over a structure, the aerodynamics involved as wind moves across a building. There's then commercial testing of building products to serve the engineering industry in Australia. And then there's also, like what we do at IBHS, there's community education. So there's a science communication, getting the word out there, training for engineers, and also just education for the general public is a really big part of what the Cyclone Testing Station does. So a lot of parallels to what we do here at IBHS in the US.
Absolutely. And here at IBHS, anyone familiar with your organization knows about our wind chamber. We love to talk about it, of course, but you do the large-scale testing at the Cyclone Testing Station a bit different. So tell me how some of your testing is done there.
Right. So it's quite different. In some ways, this is the more fundamental way that wind engineering was originally done, where you had what's called a boundary layer wind tunnel, where you make little models of buildings and put them in there. You're able to then measure pressures on the surfaces. So you know what loads different shapes of buildings will experience. But of course, these are just little models. You can put a model of a house on your lap, and fix any pressure taps or tubes that might have anything wrong with it. You can walk inside the wind tunnel, it's only say 2 meters tall, 2 meters wide. It's quite a small thing. Everything is scaled down inside. The reason it's called a wind tunnel is that when you're standing where you'd put your model and you look up the wind tunnel, you see this long array of small blocks that are arranged on the floor of the wind tunnel. And there's a fan that drags the air across this array of blocks, and it creates turbulence. So it creates the same eddies and vortices in a miniature fashion, scaled down as what we would have in the Earth's atmosphere. And we're able to measure what wind loads you might get on a house. But remember, that's just a little perspex model of a house. You've then got to translate that into real forces on a building. So then there's this translation process where you now need to build a house in full scale, create an apparatus around it, a reaction frame where you can install hydraulic rams and so on this, and pull and push on that house using the loads that you've measured in the wind tunnel. And that's some of the first tests that were done here in Australia. And Geoff, I think you were involved with some of those very first tests done at the CTS at full scale. Maybe you could describe some of those in the gigantic seesaws and apparatus that were used there.
Yeah, so the wind loads put many, many tons of pressure onto a building. The loads are quite large. So as Korah was rightly saying, we had a huge reaction frame around the building with what were effectively big hammerhead beams on the top of posts that could pull up on the roof. And so they were pulling up on the roof just like the wind pulls up on the roof. And we could instrument the roof underneath it, put load cells in it, put strain gauges in it, put deflection measurement reading devices in it, so that we could understand where the forces were going in the building. It's one thing to look at a pile of wreckage and say, okay, let's think how this pile of wreckage got here. But part of the research project was actually instrumenting a complete full-scale house, applying these loads and working out where the loads were going, working out where the highly stressed points in the structure were, and then ensuring that the designs that were coming up in order to build more wind-resistant housing were able to withstand it. So we ended up building a completely new house to the new specifications that were dreamt up after Cyclone Tracy and loading that. And then, if you like, proof testing it to make sure it was going to work. Since then, of course, there have been lots of cyclones in other parts of the country. No really big ones in Darwin, fortunately, but in other parts of the country there have been Category 3 and 4 and even 5 Category 5 cyclones that have caused damage. And we've monitored the behaviour of those buildings and found them to be much better than the ones that were blown away, if you like, by Cyclone Tracy. So this full-scale testing was the first part of the process. As Korah said, understanding how a house works, where the forces go, what the elements in the house that are loaded in an extreme fashion by the wind forces, and working out how we incorporate that into codes and standards to ensure that every house is able to withstand those loads.
And your impact goes beyond just Australia. I know you've done some work in helping other countries in the Pacific Basin. Your code work has really gone beyond the borders of Australia. So tell me some of the work that's been done, again, outside the borders of Australia and other parts of the Pacific.
Yeah, we have worked in other parts of the Pacific, Fiji, Vanuatu, a little island state called Niue. In these countries, the impact of a tropical cyclone is utterly devastating. They're very small countries. So USA and Australia are large countries, so that when Katrina hit New Orleans or when Darwin was smashed by Tropical Cyclone Tracy, that was just one small corner of the country. And the country's GDP gets a little bit of a dent from the damage, but largely the rest of the country's intact and can work together to restore that. But if you've got a small island nation, that it can be completely enveloped by one tropical cyclone or hurricane event, and that really does cause major disruption to those countries. It is, if it's important for us to have resilient housing, us to have resilient infrastructure like schools and hospitals, it is even more important for these small countries where they're operating off a smaller economic base. So it is very, very important for us to share our understandings, our findings with those countries, to help them lift the quality of their buildings so that their communities are more resilient, are able to cope with these events, which do happen, are likely to continue to happen, and may even be worse under climate change than they are now. So that we have been working with those countries on enriching their codes and standards, sharing our experience, but also working on solutions that recognize the way they do things, that tap into their own infrastructure, their own ability to do things, and maybe come up with some innovative solutions that recognize the tyranny of distance that these countries experience.
Right, all about making homes more resilient for people, whether they're in Fiji or Australia or here in the U.S. That's a big part of our mission here at IBHS as well. And I want to talk more about your work here at IBHS, Korah. I've heard you talking to prospective wind engineering students that have toured our chamber, and you talk about IBHS's wind tunnel being a wind engineer's dream. So, what is the dream? Why is that the dream?
Right. Yeah. If you've ever been inside IBHS test chamber, you might straight away realize that, and also get an idea of why I moved to the other side of the world to work here at IBHS. I described initially the boundary layer wind tunnel we have in Australia, where it is 2 meters by 2 meters, maybe about 20 meters or so long. You can climb some stairs, jump inside. It's not that big. There's one large fan behind you. The IBHS test chamber is about 6 stories tall and about the same size wide, and an array and almost an amphitheater-like look of 105 fans. That produce that consume about 35 megawatts of power when they're going full speed. So it's an incredibly large and incredibly powerful facility. And being in there is quite extraordinary. And why is it the wind engineer's dream? Well, wind is an extremely hard thing to bring into the lab, right? We initially needed to make do with little perspex models that we take some measurements on, we do some scaling, then we use hydraulic rams and push and pull on buildings. But wind is far more complicated than that, right? You have turbulence in the atmosphere, and as that moves over the roof of a building or the walls, it creates even more turbulence. You have eddies and vortices that streak across the roof. High suction pressures here and there, positive pressures in other places. These fluctuate rapidly throughout time. And how you can simulate this just with hydraulic rams and other machines in a laboratory, it's really hard. Also, an issue with using traditional engineering laboratory equipment is that when you start failing things in the lab, when things start to come apart, the load on those actuators drop down as things slip and pull away. But wind is very unforgiving in that way. You don't get a break at all. Once when things start to pull away, that wind pressure doesn't stop at all. And so that's why the dream has always been to test real structures in full scale with real wind as well in full scale, to not only measure loads throughout the structure, but also understand how things come apart. And that's what we can do here at IBHS. The other reason why we test in full scale is that certain things don't scale down very well. In the wind tunnel, in the boundary layer wind tunnel, when you scale things down to 100 times their normal size, or 50 times, or sometimes 400 times their normal size for larger buildings, small gaps and small features of the buildings are hard to capture. You've scaled the building down, but you've not scaled the molecules of air down. That air is still just as viscous as it is in full scale. So there's certain things that are very hard to model at a very small scale. And one of these things is solar panels. And that's a project that I'm working on right now. And it's in many ways also a collaboration with testing that's done at James Cook University. testing solar panels at model scale has been traditionally the way it's been done, and it's a very effective way to test multiple configurations. But understanding where things work well and where things don't work well when you're working at that scale, that's something that we really need to understand more with. And so we're very lucky to be able to test a full-size building with real solar panels, with the actual geometry they have here in the test chamber, and take those measurements. We can understand, which parts of a solar panel array are more vulnerable, which parts are not so vulnerable. And also we can make sure that any model scale testing that we do, which is what we often need to do, can be validated as well. And it's very exciting work to be able to work with full-scale wind data as well.
I've got to say, we have envy of your facility, Korah. It is really great working with you because of that facility, because of the skill of the people using it, because of the work that you're able to complete using that facility. It's just magic.
All right, so solar panels is one of your projects. You're also working at another project. We hit on this a little bit earlier. We talked about, how a home can survive because of a good building code, but still be unlivable due to other factors like water intrusion being a big one of those. This is a subject area where there's some gaps in the research. And Korah, you're working on a project right now to help close some of these gaps, especially when it comes to how windows and doors stand up to water intrusion. You worked on a very similar project in Australia. So tell me about your work in Australia and what you're doing here at IBHS in this space.
Sure. Yeah, this is actually another longstanding collaboration we've had between the two research organizations. And to paint a picture a bit more, like you said, you can have a house totally intact structurally, but still with a lot of water damage that makes it unlivable. One of the houses that we surveyed after a damage survey after Tropical Cyclone Debbie in the Whitsundays in Australia, it was a 2-story house with a window that blew in on the top floor. And just from that one window blowing in, the amount of water that got in then found its way into the ceiling of the next floor down, found its way all through that roof structure. That floor structure. It was extraordinary. It's just a disproportionate amount of damage that can happen in a house just for one window blowing in. And this can happen sometimes not even with the window blowing in. You can just have water leaking through the window. And that's the kind of testing that we're doing here at IBHS, and what we were doing back in Australia. And the way I describe this is to really understand, how does a leaky window leak? How does it actually leak? Is it just because there are holes in it and water comes through? Well, not really. There's a lot more going on. There are, if you take a cross section of a window, those extrusions that form its frame have a multitude of air spaces and tracks and weep holes that are meant to guide water out of the building when you have condensation. But all of that acts in reverse when you have a wind pressure on the outside, and at the same time have rain falling on the window. So we have, from looking at it on the outside, it almost looks like a cupboard. It's a pressure box with a window or door installed in front of it. You open that cupboard, you open up that door, and you'll see an array of spray nozzles arranged on a rack there. And so that's the rain that's outside the window. Once you've sealed up that pressure box, we can connect that pressure box to what are called pressure load actuators. So these are very powerful blowers that don't just produce a constant pressure. We can actually take some data either from the field, from some anemometers put out in front of a cyclone, or from the test chamber or the wind tunnel, and program in a fluctuating pressure trace. One of those, as Geoff described it a few minutes ago, the positive pressures that a wall might experience during a storm, that rapid those rapid fluctuations, the buffeting pressure on a wall, can be programmed into that pressure chamber. And with the concurrent application of water, we can really test the limits of a window to see where water emerges through it and finds its way into a building, onto our carpets and furniture, and sometimes into the story below, causing a huge amount of damage. A really important part of that is not only just having this pressure chamber, but also to really bring people into the peril and to create a compelling demonstration of how water damage can occur. It's a really big part of the science communication we do here at IBHS now. So in a way, it's a setup that looks a little bit like a diorama. It's going to be dressed up like a hotel room or an office space with furniture, some carpets, and so on. And Rachel, I think you've been really helpful for us as channeling your interior decoration skills to help us actually select some of these items to create a little demonstration room for how water damage can occur as well.
Right. We love the science, but we want to make it as realistic as possible here at IBH. So we just add that little extra touch to help people envision the situation in real life. So yeah, a little tease of what's to come. We're looking forward to seeing more on that project here at IBHS over the next few months. All right. Well, we're going to wrap this episode up. Really interesting story here. A really interesting conversation. Of course, I think we've learned that a lot has been accomplished. Australia, of course, has adopted a national building code. The U.S. hasn't quite done that yet, but we've worked to improve building codes, especially in the wake of Hurricane Andrew. Both of these tackle life safety, and in areas where the code is good, people can survive storms in their homes. And here at IBHS, of course, we're also trying to tackle that loss reduction problem with our fortified program. Again, not only helping people survive these storms and these hurricanes, but getting people back into their homes in the immediate aftermath. So still work, of course, plenty more work to be done. So I just want to ask you both as we wrap up, what gaps do you guys see that need to be filled when it comes to strengthening homes and buildings against severe weather, whether that's here in the United States, in Australia, or elsewhere for that matter?
The resilience piece that Korah has mentioned is really, really important. As he rightly said, our building codes and standards preserve life safety. If we're thinking about community function, then for a community to function, the buildings have to be able to function. And so in order to keep buildings functioning after these kind of events, we need something more than just the basic life safety. We need Code Plus, we need Fortified, we need resilience built into our buildings, particularly our critical buildings, so that after it has happened, we can press the button and it's business as normal. Things like hospitals, schools, really important for those to have resilience. Even homes, if we want to have a workforce clocking in for work soon after the event, then their homes have to be safe. Their homes have to be functioning. And that's the core of the resilience piece. Resilience safeguards community function. So we need to broaden our thinking to how do we keep our communities functioning by keeping our building stock, our infrastructure functioning after these events have been through.
Right. Yeah. Just to touch on that, Geoff, a saying I picked up on back at James Cook University is that you could say that there's no such thing as a natural disaster. There's either just bad weather, and then there's engineering structures or infrastructure that may or may not be up to the task. If our structures, our infrastructure, our communities are resilient enough, it is just bad weather. It's not a disaster. And a big part of that is the importance of building regulations, even though it's perhaps the driest topic in the world, is instrumental. Building safe and economical houses that can weather storms is absolutely essential, right? Australia has been doing it for a long time. Florida is really good at it. We have the fortified program as well. We know how to design a house to stand up to severe weather. These are not concrete bunkers. These are not concrete bunkers at all. These are light frame structures like any other, except they have the detailed engineering calculations performed, that tie-down chain that keeps the structure together. It's in many ways a triumph of engineering that we can keep these light frame structures together. We know how to do it, but it's really our building regulations that will really keep our communities safe. And so that's really the next wind engineer's dream of mine, is really that science communication, that advocacy that we do, both at the cyclone testing station and here at IBHS, is to use the engineering, the hard yards that we put in already, and to just get that out there and get that entrenched and part of our communities.
All right. Well, Geoff, Korah, thank you so much for joining us on this episode of Disaster Discussions. We really enjoyed having you. And Geoff, I guess the both of you are our first international guests on the podcast. So I want to thank you for joining us today.
Well, thank you too. I've really enjoyed it. And it's been wonderful talking with Korah again. I really enjoyed it, Korah.
Yeah, likewise, Geoff. Always good to catch up with you. And thanks, Rachel, for having us on board.
Thanks for listening to the Disaster Discussions podcast. Join us next month for a new episode. For more on IBHS's ongoing research efforts, visit ibhs.org.